Hello and welcome back. My name is Jack B. And as always, thank you for viewing my video. I recently came across an article that piqued my interest, and of course it led me down some rabbit holes. It was a new concept as to how the human brain senses or perceives reality. Before going on, there are a few terms that might need some clarity. Number one, the conscious mind contains everything you are currently aware of, such as active thoughts and sensory perceptions. It is slow, uses a lot of energy, and can only process a small amount of information at any given time. Number two, the subconscious mind is your brain's automated processing center for accessible habits and background memories. You can easily pull these thoughts into your focal awareness when needed. It acts as a bridge, holding accessible information and automated habits. It operates 24 hours a day and 7 days a week, and drives a massive percentage of your daily automatic behaviors and reactions. Number three, the unconscious mind holds deep, hidden drives, hidden traumas, repressed memories, and biological functions that you cannot actively access or control. It is the deepest layer which contains inaccessible drives. While you aren't directly aware of it, the unconscious mind heavily influences your emotional responses, anxieties, and overall behavior. This is the largest domain of the mind. It operates continuously and heavily shapes the symbols and hidden meanings in your dreams. The new breakthrough concept on how the brain constructs reality is called predictive processing. The thought is, rather than the brain passively recording the world like a camera, it acts like an active analytical computer. It constantly generates best guesses, predictions, about what it expects to experience. It only uses outside sensory data to correct errors in its predictions. All the inputs, vision, sound, touch, smell, and taste, to the brain are received by the subconscious mind and sorted through and passed on to the conscious mind. They can be received simultaneously or individually. Recent breakthroughs have expanded on this concept, shedding light on exactly how the brain decides if an experience is real or just imagined. Neuroscientists at University College London discovered that the region or hub of the brain, called the fusiform gyrus, distinguishes imagination from reality. The fusiform gyrus is located on the basal bottom surface of the brain. It spans across the temporal and occipital lobes and sits behind the temples. Both real perception and vivid mental imagery activate this region. If the combined strength of this sensory activity meets certain criteria and crosses a certain threshold, the brain's decision-making center, the anterior insula, classifies the experience as objective reality. Because of this mechanism, some neuroscientists refer to perception as a controlled hallucination. What we see, hear, and feel is essentially our brain's internal prediction that has been locked in and synchronized with outside sensory information. When the prediction is strong enough, we accept it as reality. Hallucinations can be perceived as real when the brain's reality-checking threshold breaks down, such as when the fusiform gyrus fires, as if a real physical object were present. This offers new neurological clues into conditions such as schizophrenia, where patients may struggle to separate internal thoughts from external reality. This can also explain common quirks of human perception, everyday misperceptions such as mishearing song lyrics or momentarily mistaking a shadow for a person. Your brain's internal model temporarily overrides the weaker incoming sensory signal. The brain's predictive processing works on a hyperfast subconscious timeline, actively anticipating the world approximately 80 to 400 milliseconds before they consciously register. This allows the brain to compensate for neural transmission delays and operate seamlessly in real time. The speed of this mechanism depends on the type of information being anticipated and processed. The brain's regions actively anticipate upcoming words or syllables in milliseconds. When hearing speech, the brain anticipates what will be said next, preparing the neural networks to process expected sounds faster while spiking in activity if a word is surprising. The brain anticipates motion roughly 80 to 100 milliseconds ahead when tracking moving objects. This compensates for biological delays, transmission of signals, so humans can seamlessly track moving targets. Visual processing occurs in as little as 13 milliseconds for flashes of static images. In certain situations, such as applying the brakes of a vehicle, the brain initiates physical actions based on predictions up to 400 milliseconds before a person becomes consciously aware of deciding to act. While subconscious prediction happens in milliseconds, the conscious processing of information, translating those sensory predictions into purposeful, reasoned action, is surprisingly slow, operating at an average limit of about 10 bits per second. The 10 bits per second metric refers to the processing speed of conscious human thought, not its duration. This rate describes the maximum bandwidth at which the human brain can make decisions, store information, and process deliberate actions. Research by neuroscientists at Caltech found that regardless of whether you are reading, playing a video game, or memorizing cards, our conscious thought, or deliberate cognitive throughput, caps out at about 10 bits per second. Even though our conscious thought is limited to just 10 bits per second, our subconscious sensory systems, vision, hearing, touch, smell, and taste, gather environmental data at a rate of up to 1 billion bits per second. The brain acts as an extreme filter, reducing the billion bits of sensory data down to a trickle of just 10 usable bits to prevent us from being overwhelmed, allowing us to focus on one deliberate thought or action at a time. One is constantly filtering out 99.99999% of what your eyes, ears, and skin take in to prevent overload. Real-world examples of 10 bits per second are 1. Making one meaningful choice, for example, a move left or right, every second or two in a video game. 2. Manually typing or keying Morse code at a steady pace of about 1 or 2 letters per second. 3. Formulating 1 to 2 words of thought or English text per second. As previously stated, the human brain can process and identify an entire meaningful image seen for as little as 13 milliseconds. This means the visual system can register complex concepts, such as recognizing a picnic or a smiling couple, at speeds vastly faster than a single blink of an eye. While the 13 millisecond threshold is the fastest recorded speed, practical recognition often takes longer depending on the context, such as familiarity of the image. We recognize faces and highly familiar objects much faster than obscure, abstract, or complex scenes. Image, detail, and contrast. Minimal or highly blurred images require more processing time, sometimes taking seconds for the brain to parse the visual data. Prior knowledge. If the brain is primed to look for a specific target, for example, finding the flower, identification happens significantly faster than when viewing an image completely unfocused. The speed at which we recognize an image relies on a swift, continuous feed-forward cascade through different brain regions, starting with light entering the eye. The optic nerve projects to several different areas in the brain. Approximately 80 to 90% of the nerve fibers travel to the thalamus to form the conscious vision pathway. The remaining fibers branch off to other regions to manage subconscious reflexes, sleep cycles, and eye coordination. Light hits the eye, retina to the optic nerve, and translates into electrical signals. The electrical signals then go to the optic chiasm, where the signal is split and routed to 9 primary visual nuclei. The brain's visual processing center, the visual cortex, starts responding to the visual stimulus and extracting basic features, like lines and shapes, as early as 80 milliseconds. Even before we consciously see the image in full detail, the brain has already categorized the object through conception recognition. Studies show the brain can recognize images exposed for just 13 to 14 milliseconds without needing feedback from higher-level cognitive areas. While the recognition itself happens in a flash, the total reaction time typically takes the brain about 400 to 500 milliseconds to fully react to what is seen, such as reading a road sign and swerving or pressing a button. The majority of this time is eaten up by the brain sending motor signals to the rest of the body. Experiences such as driving to a location and not remembering the drive occur because the brain relies on procedural memory for highly familiar routes. Instead of recording every mundane detail to short-term memory, the brain essentially shifts into an automated autopilot to conserve mental energy, filtering out repetitive and expected visual information. While you may feel like you zoned out or completely lost time, your subconscious mind and eyes remain actively focused on driving conditions, allowing you to steer, brake, and navigate safely. There are several reasons that cause the brain to bypass memory creation during a drive. It happens most frequently on familiar routes where there are no surprising or atypical events for the brain to process and store as new memories. Just as you don't actively think about how to walk, your brain's subconscious hub, the basal ganglia, takes over the physical act of driving, freeing your conscious mind to daydream or think about unrelated things. The brain processes words to the conscious brain slower than it processes images. The processing of images and words involves different neural pathways and speeds. The brain processes images holistically and can recognize a visual scene in as little as 13 milliseconds. Up to half of the human brain's resources are dedicated to visual processing, making it our most optimized and innate sense. Words are essentially intricate collections of shapes, letters, meaning the brain must work harder to decode them. Reading requires a linear, sequential decoding process that involves recognizing shapes, translating them into sounds, and then interpreting the meaning. Because images are processed instantly and in parallel, they are also significantly easier for the brain to store and retrieve from memory later. When the brain processes images holistically, it perceives the overall shape, meaning, and structure of an image as an integrated whole, rather than analyzing its individual fragmented pieces, like lines, colors, or pixels, one by one. The brain grasps the gestalt, or big picture, instantly. Holistic processing can be broken down into these core mechanisms. The brain synthesizes features into a complete concept. For example, when looking at a human face, you see the unique identity of a person rather than simply processing a collection of eyes, a nose, and a mouth. Because the brain merges parts into a single visual representation, it is incredibly difficult to ignore one part of an object without the rest of it interfering. You can train your brain to process non-facial items holistically. Experts in certain fields, for example, radiologists analyzing an X-ray or car enthusiasts identifying a specific model, rely heavily on this rapid global extraction of information to interpret complex images. Science explains the reason for processing images faster than words is due to survival adaptation. Sight has been critical to human survival for millions of years. Reading, however, is a relatively recent cultural invention that hijacks parts of the brain originally built for visual object recognition. The brain dedicates nearly half of its neural resources to visual perception. Not only do we recognize images faster, but we also retain them much better. We remember visuals far more effectively than reading the exact same descriptive paragraph. The human brain recognizes and processes the meaning of a single word in about 150 to 200 milliseconds, still fast at a fraction of the time it takes to blink. This lightning-fast process breaks down into distinct, measurable stages of neurological activity. Neurological studies, including research from NYU and Scientific American, outline the millisecond by millisecond process of comprehending a word. From 0 to 100 milliseconds, the brain's auditory or visual cortex receives the raw data. The visual form of the word, or the sound wave of spoken speech, is encoded. From 100 to 150 milliseconds, distinct sounds or letters are parsed. In spoken language, high gamma brain waves drop sharply at a word boundary to signal the end of a word. While reading, the brain recognizes the basic linguistic structure of the sentence. From 150 to 200 milliseconds, the brain starts retrieving the actual meaning and grammatical context of the word from the left anterior middle temporal lobe. The recognition of an individual word happens at lightning speed, but the full sentence comprehension relies heavily on context and familiarity. The brain actively predicts upcoming words. If a word is highly expected, the brain can recognize its meaning even faster. Rapid word processing peaks in our 20s and 30s, but studies, such as those from the University of Iowa, show that by our mid-40s, processing spoken words can take up to a fifth of a second longer due to the sheer volume of vocabulary the brain has to sort through. The speed of a physical touch to your brain relies on several specific factors such as physical distance, nerve fiber type, and cognitive processing. It takes about 20 to 50 milliseconds for a physical touch to register at the primary somatosensory cortex. However, the time it takes to become consciously aware of the touch can stretch to 100 to 400 milliseconds as the brain takes time to filter, organize, and integrate the sensation. The timeline of this process unfolds in a few distinct phases. 1. Peripheral travel time, 5 to 20 milliseconds. Sensations begin when touch receptors, mechanoreceptors in your skin, fire signals. These impulses travel through fast, myelinated nerve fibers up the spinal cord. Depending on where you were touched, this takes only 5 to 20 milliseconds. 2. Subcortical relay, less than 5 milliseconds. The nerve signals enter the brainstem and travel to the thalamus, which acts as the brain's major sensory relay station. This relay happens almost instantaneously, often taking less than 5 milliseconds. 3. Primary cortical registration, 20 to 50 milliseconds. From the thalamus, the signal is projected to the primary somatosensory cortex. When measuring brain waves, scientists typically see initial touch responses here in about 20 milliseconds for a hand and up to 40 milliseconds for sensations from the feet. 4. Conscious perception, 100 to 400 milliseconds. While the brain detects and localizes touch instantly, conscious awareness is not immediate. The brain must integrate secondary signals from the secondary somatosensory cortex and other associative regions. The brain processes time in distinct time slices, and the full emergence of conscious perception can take up to 400 milliseconds. Pain and touch utilize distinct parallel pathways to reach the brain. Touch signals travel via the dorsal column pathway, ascending the spinal cord on the same side, while pain signals use the spinothalamic tract, crossing to the opposite side of the spinal cord almost immediately. These pathways aren't entirely isolated. Because they both route through the thalamus and the somatosensory cortex, they influence each other. This overlap is the reason behind the gate control theory, why rubbing a stubbed toe or an aching joint activates touch receptors that send competing signals, effectively dampening or distracting the brain from the pain signals. The pathway of smell to the brain is also interesting. Once odor molecules enter your nose, it takes just 110 to 150 milliseconds for the brain to detect and decode the scent. This process is so fast that mammals can actually begin to recognize a smell within the first 50 milliseconds of inhaling it. This lightning-fast connection to emotional and memory centers is why certain smells can instantly trigger intense, vivid memories before you even consciously realize what you are smelling. Airborne chemicals, molecules, enter the nasal cavity and bind to sensory receptors on the olfactory epithelium. This triggers electrical signals that are sent directly to the olfactory bulb, the brain's odor processing center. This sensory pathway progresses through highly specific physical structures. Odor molecules bind to microscopic cilia, hair-like structures called receptors located in the upper nasal cavity. Axons, nerve fibers from these neurons pass through tiny, sieve-like holes in a bone at the base of the skull called the cribriform plate. These nerve fibers connect directly to the olfactory bulb, located just above and behind the nasal cavity at the base of the forebrain. Located just behind the olfactory bulb, the piriform cortex is the main hub of the primary olfactory cortex and is responsible for consciously identifying and categorizing what you are smelling. Signals are sent directly to the limbic system, amygdala, and hippocampus to trigger deep emotional responses and form vivid memories. This explains why a certain scent can instantly bring back a strong childhood memory. The orbitofrontal cortex integrates smell information with taste data to create the perception of flavor when you eat. In summary, the information speaks for itself. I find it fascinating that the new concept defines our sense of reality on the analytical predictiveness of the subconscious, anticipating what will occur next, and then validating it with sensory input, adjusting the decisions before we realize it in our conscious mind. Well, these are my thoughts for today. And again, whether you agree or disagree, please verify the information presented. Thank you. And until next time, take care and be safe.
Ah. No, Kevin. Me na do it.
Ooh.